Hi everyone, in this video I'm going to give a presentation for the ICSGRC 2020 conference about our work entitled Real-Time Baby Crying Detection in a Noisy Everyday Environment. So, in the first months or even the first few years of a baby's life, crying is a child's major means of communicating needs or distress. And typically, parents or caregivers monitor the child and are able to recognize the baby's cry with ease and with great accuracy. But this requires the constant attention of the caregivers. So having an automatic real-time baby crying detection algorithm could help alleviate the burden of parents and caregivers, especially during situations that it's not possible to constantly monitor the child. But besides that, these automatic crying detection algorithms are also an essential component in crying diagnostic systems, where these diagnostic systems can help reveal conditions of the child that untrained ears are unable to do just by listening to the crying. So, for example, when a baby is crying and the automatic crying detection algorithm detects the crying, these crying signals can then be segmented and passed on to these classification algorithms that can determine conditions of the child. So, for example, they can be used to classify emotions of the child. So whether the baby is sad, happy, or angry, or it can also be used to tell why the child is crying. So for example, if the child is crying due to hunger, tiredness, discomfort, or pain. And other than that, baby crying sounds also have the potential to be used for pathology or disease diagnosis. So just from purely analyzing the crying sounds, we may be able to detect the presence of different diseases, such as neurological diseases like sepsis or meningitis, or respiratory diseases like asphyxiation, and also thyroid diseases like hypothyroidism. So, crying detection algorithms are important in that they play a role in building these classification systems that help tell more about the child's well-being than the human ear can. So, because of this, crying detection algorithms have been the subject of research for many years. But majority of previous works focused on pre-recorded audio, which were then tested off-site or offline testing. And some of these audio were also recorded in controlled quiet environments. For example, they were recorded in clinics or in the laboratory. And these environments don't reflect actual real day-to-day scenarios in our lives, because children are usually at home or at daycare centers or at schools where there may be a lot of background noises, like having adults talking in the background or having the TV or music playing in the background. And with the presence of these noises, it becomes harder to isolate the baby crying sounds. And especially for classification systems that are time sensitive. So for example, for detecting asphyxiation, having a real-time crying detection algorithm that is able to function in our noisy everyday environments is very important. And so our study proposes a crying detection algorithm that can detect baby crying in real time and in everyday noisy environments. So for real-time crying detection, having a short processing speed is very crucial. And with this in mind, our proposed detection algorithm detects crying by extracting and analyzing 5 features that is quick to process but also carries important information about the crying sounds. So the 5 features used in our algorithm are the average frequency, to reveal where the frequency band of the sound mostly stays, the pitch frequency, because crying sounds have a unique pitch from non-crying sounds, the maximum short time energy acceleration, to detect bursts of crying after silent periods, the zero crossing rate, which is useful for detecting voice sounds from non-voice sounds, and finally the male frequency substral coefficients, or MFCCs, which makes use of the male scale frequencies that better emulate human hearing. So this is our proposed crying detection algorithm. And in this algorithm, the recorded sound is processed on a second-by-second basis, So this means that for every 1 second segment, the signal is pre-processed. Then the signal goes through feature extraction, where the 5 features that I've mentioned are extracted from the signal. Then from the calculated features, a score is awarded for every feature based on whether the feature surpasses a certain threshold. And finally, if the total score of this 1 second segment is equals to or more than 3, it is then classified as crying. But if the score is lower than 3, it is classified as non-crying. So, to train and to test this crying detection algorithm, we conducted 3 experiments, where the first experiment is for training the algorithm. The second experiment then tests the algorithm in offline detection. And finally, the third experiment tests the algorithm in real-time or online detection. So in the first experiment for training, we obtained clean crying and non-crying samples from this depository. And we then used these clean samples to train the algorithm on the thresholds of each of the 5 features. So based on the distributions of each of the crying and non-crying features, these distributions were used to set the thresholds in the algorithm. So once the thresholds were set, we then moved on to testing, where in the second experiment, we tested the proposed algorithm in offline testing. So here, we collected clips of crying and non-crying videos from YouTube and extracted the audio clips from these videos. So these videos were taken in noisy environments such as at the daycare center or at home with the TV playing in the background. And the algorithm was applied on these noisy samples. And we found that the algorithm was able to achieve an accuracy of 89.2%, sensitivity of 85.04%, specificity of 90.77%. And finally, in the last experiment, we conducted real-time detection using the proposed algorithm. So for the audio samples in this final experiment, what we did was we randomly selected segments from the different YouTube video samples used in the second experiment here, and we merged these randomly selected samples to form custom noisy samples containing both crying and non-crying segments. So we used these custom noisy samples for online testing, where we played the custom noisy samples through these set of speakers and recorded the playback using this microphone for real-time detection. So let me show you a video demoing this experiment. So I'll play the video once and then I'll give a brief explanation afterwards.
I'm from the northwest of England. I live in London. What do you like the most about London?
I love how diverse it is. I think you can walk out of your door.
School. Hey Desh, need school leave tomorrow pola.
Okay, so let me briefly explain the setup here. So to simulate a noisy environment for real-time crying detection, we played the custom noisy samples through these speakers and recorded the sound using this microphone. And the microphone was then attached to the laptop. And in the laptop, we then used MATLAB to process the recorded sound on a second-by-second basis. And if the 1 second segment is identified to have crying sound, it is labeled with a crying notation. And if there is no crying sound detected, then no annotation is displayed.
Hey Desh, need school leave tomorrow pola.
So that was the setup for our third experiment, which we used for online testing. And in this online testing, we found that the proposed algorithm achieved an accuracy of 80.77%, along with a sensitivity and specificity of around 78 and 84%. So, comparing the proposed algorithm with previously published works, in offline testing, we were able to achieve comparable accuracy with other previously published crying detection algorithms. Whereas for online testing, there are actually limited related works in the current literature, but when comparing our proposed algorithm with a closely related publication, our algorithm was found to outperform this publication, as our proposed algorithm achieved a higher accuracy and required a short processing time of only 25 milliseconds. So for real-time testing, we found that the performance of the detection algorithm depended on the quality of the recorded sound. So it may be possible to improve the accuracy of the algorithm with better quality speakers and microphone. So to briefly conclude, the proposed crying detection algorithm was able to detect crying in noisy environments and in real time with relatively high accuracy. And successful implementation of the crying detection algorithm could potentially aid in the development of classification or diagnostic systems, such as for disease diagnosis. So this could potentially pave the way for monitoring the health and well-being of children in real time and in a non-invasive manner by purely analyzing children's crying sounds. So with that, these are my references, and I would like to end my presentation here. Thank you.